Hi everyone. In this section we're going to work on two topics that I don't think will be too hard to get a handle on. So first we're going to talk about arc length. We're going to work up a formula for finding arc length, and then we're going to talk about area between curves, which is like a tiny baby step from finding area under curves. Okay, so first we want to talk about arc length. So let's say we're looking at this graph right here, and we're interested in how long the curve is. Let's say we're interested in going from A to B. And this could be a really simple question if our function was constant, or any sort of straight line, in fact. That would be easy. That would be easy. For the not horizontal line, the not constant function, we could just draw a triangle. If we had half a circle, that would be easy. As we get into any other sort of curve, it starts to get really tricky. So we're going to start a recurring theme for this course in general, but especially for chapter 3. When we have a question like that that's kind of tricky, we slice the curve up into little pieces. And we say, well, let's zoom in, and this isn't that little, but just so that I can draw it, pretend it's really, really little. And if we zoom in on that piece, it's going to look really close to a straight line. It's going to look really similar to a straight line. And the more we zoom in and the smaller our slices, the more it becomes basically a straight line. And that's a property of a function being differentiable. If your function has a tangent line, that means that if you zoom in enough, it begins to look identical to its tangent line. Okay, so we're going to look at this little piece right here, and we're going to say, okay, great, so now it's a straight line. How do I find the length of a line segment like that? And the answer is we do what we talked about before. We draw a little triangle, and this is a right triangle, which makes me happy. Okay, and then we need to, I don't think I want to get an angle involved. You could use angles for right triangles, but here I think what I want to get involved is that the base of this triangle is a tiny, tiny slice of x values, right? That's a little, whoa, that's a delta x. And the height of this triangle is a delta y. So if we want to find, what do I want to call it? I'm going to call it a delta L, this little bit of length right here. We're going to say that, I want to call it a delta L or an L. I'm going to call it an L sub I. It is a little tiny change in length, but I think that we're going to add all these up. So calling it an L sub I will make more sense for our notation. So we're going to say that L sub I squared is equal to a delta x squared plus a delta y squared. And that means that our L sub I is equal to the square root of delta x squared plus delta y squared. Okay, and this is a formula, but it doesn't really help me with actually calculating this. What is my delta x? What is my delta y? How are they related? So I'm just going to do a little algebra until we come up with something that looks a little more familiar. So the first thing I'm going to do is actually factor out, let me make sure I factor out the right thing. I'm going to factor out a delta x squared under the square root. So under the square root, I have delta x squared, and that's going to leave me with a 1 plus a delta y squared over delta x squared. And I can do a couple of nice things here. One is I have the square root of a perfect square, so square root split over multiplication. I can go ahead and take the square root of the delta x squared and say, okay, that just leaves me with a delta x out in front of the root. The other one is, if I look at this as a delta y over delta x squared, I start getting closer to notation I want to see. Okay, so this is the beginnings of our formula. That's how we're going to calculate an L sub I, and I'm actually going to rearrange just a little. I'm going to put this delta x out at the end. So if we want to get the entire length of the curve on AB, on AB. We're going to add up all of the L sub i's. And let's just say we did n subintervals, 1 to n. We're not going to start at n, we're going to stop at n. We're going to add up all of these. And, oh, I didn't leave myself very much room there. So that would get us an approximation of the entire length. If we want to make that not approximate but exact, we then need to take the limit as n goes to infinity. So we need to cut into infinitely many subintervals, making our delta y and delta x infinitely small. And as soon as that happens, when we take this limit of our infinite sum, we should be getting our integral, L equals, and each term is going to be a square root of 1 plus, when we let n go to infinity and delta y and delta x become infinitely small, they become dy and dx. And that is our arc length formula. dy dx is exactly what it was in Calc 1. This means if you want so if this is y equals f of x, if you want the length of this curve, we would say, okay, then we're going to take the integral of the square root of 1 plus f prime of x squared. We're going to integrate with respect to x from a to b. So basically what's happening here is the f prime is what tells us how steep the curve is at that point, which is going to tell us something about the relationship between our delta x and our delta y. So that's determining the length on any individual segment. Okay, so this is a formula. Memorize it. You should know this when you sit down for your final. So we'll work through some examples and we'll also talk about area. But this is really the memorized piece for this section. I think area is going to be really intuitive. Thanks for watching.